Today we will discuss big O notation and how we use it for calculating time complexity of any algorithm. Let's take an example. So now look at this algorithm. If the input is even, the iteration is only one statement. If the input is odd, the iterations is n times. There will be n iterations. So if we can observe through, we have for the same algorithm, based on our input, we can say the first one, that means if input is even, can we say this is an best case, and if the for the second it is odd, it is having an iteration, so this we can say as worst. Okay, so let's understand with one more example. Suppose here we have one sorting algorithm. For the test case 1, I have input 1 2 3 4. Suppose I have to sort in small to big. See, for the test case 1 it's already sorted, so can we say this is an best? So here I can say it represented by omega. And for test case 2, I'm taking the input 4 3 2 1. See, it here I need to again sort from small to big, so it is the worst case, and we represent as big O. And the test case 3, let's take 1 2 4 3. Here this is, we can say, average, and we will represent as theta. So what we can say here, in real time solving problems, we should always deals with worst case. Like quote says, to be best you should be ready to handle the worst. So we will take big word notation. And now let's discuss the rules for how to calculate big O notations. Now here these are the rules. Let's Rule number 1, calculate number of iterations based on inputs. Yeah, we did it. We are considering the iterations, whatever, for loop, while loop, do while, anything. Now second, neglect lower terms or keep only higher order terms. What it means, let's take an example: n square plus 10 and any polynomial. Here, if n is 10, and let's also take let's 10 equals to 100. Also let's take n equals to 10 power 4. Now what is the percentage of its small n in n square? See, in n equals to 10, it is 100 plus 100, right? So it's to complete 200. The contribution of n is 100. The year it is 50 percentage. And then next it is 10 power 4 plus 10 cube. Here it's approximately 90 percentage. Next 10 power 8 plus 10 power 5. Now the contribution of n in n square is 0.1 percentage. So we can neglect the lower terms, or we can keep only higher order terms. And similarly, just take for the larger inputs, take any polynomial, compare them, and you can see that you can neglect constant coefficients. Now uh, we will do, in real time solving problems, we will face loops and recursions. Now I will solve for you how can we calculate time complexity for the loops. Let's take an example. Example 1. Here, how many times the statement will run? I equals to 1, I equals to 2, I equals to 3, I equals to 4, and so on, n. So the statement will run n times. Can we say this as order of n? Yes. So now, yeah, for example, if you take the with instead of I plus plus, if you take I equals to I plus 2, so it will increment by double. So what it will be? N by 2. Yeah, this already we have observed in our part 1. So here it is n by 2, and we will neglect this coefficient, and we will take order of n. Now here observe I equals to 1 to I less than n, and I equals to I into 2. So here observe the pattern for iteration 1, for iteration 2, for iteration 3. For iteration 1, it is 1 is equal to 1 into 2, so we can write as 2 power 1. And iteration 2, here I is always 2, so 2 is equal to 2 into 2, that is 2 power 2. And for I equals to 3, here already it is 4, so 4 is equal to 4 into 2, that is 2 cube. So for iteration k, it will be 2 power k. So what did it means? So to the 2 power k, we'll have n iterations, and if we write in logarithmic, log 2 base 2 log n is equal to k. So can we say the time complexity for this order of log n? Yes. Now let's take example this one. For it is the two for loops, nested for loop. So here for I equals to 1, j runs for 1 to m times, and I equals to 2, again m times. So similarly for I equals to n times, it will run m times, that is it's nothing but n into m. Yeah, the time complexity big O of n into m. So similarly, we can calculate with this approach for various time complexity of the algorithms. So if we observe in the graph, looks like in the image, it will be like this. It will be order of n, order of log n, order of n, order of log n. Like this, the graph you can observe for the larger inputs. So if we see here, like how it helps means, when you solve any DSA problem, there you can observe if the algorithm 1 is coming as n square, and algorithm uh 2 it is coming and log n, which one you will pick? Obviously log n, because log n is least time complexity. So in this way we can calculate time complexity of data structures. So now we will for time complexity for recursions. So recursions is very easy. For example, look at this statement in the recursion. Let's suppose this is some t of n times it will run, and the statement is one time, and function it is again recursion, so it is t of n minus 1. So what we can say, t of n is equal to t of n minus 1 plus 1, right? For example, t of n minus 1 we can calculate by back substitution. So here t of n minus 2 plus 1. So we can say that t of, how can we say, so we can say that here it will be 2 when we substitute. So it will be like t of n minus k plus k, that is when n minus k is equal to 0, 1 plus n. So we can say it is order of n. So similarly it is order of n, and for t of n minus 1 plus, if you calculate you can get as order of n square. If you calculate this part, you will get as order of n into log n. Just take this as an example, do back substitution. Here 1 means just one statement, here n means there will be one loop. In log n we already calculated how it will be. So in this video we have discussed time complexity with big O notation. In next video we will discuss space complexity.